and that you're ready for the class this morning. Also, tell the rest that have not joined us yet to join us so that we can start now. I think we'll just start off, or we give them like 7 minutes. It's 8:53, so that we begin at 9 as we wait for the rest to join us. I cannot see Margaret. I cannot see Stacy. I cannot see these other guys. So tell them to join us. So we start at 9. So let's look at types of search algorithms. Types of search algorithms. So for an agent to be able to solve a problem, it has to use one of the different types of search algorithm to search and traverse through the different solution nodes, or what you call the the nodes, right? The optimal, the possible solutions, and it uses different kinds of algorithms. Now these algorithms can be divided into two: uniformed or blind search and informed search algorithms. Informed and uninformed. This is not uniformed, it's uninformed, sorry. It's uninformed search algorithms. Uninformed search algorithms. So let's begin with uninformed search algorithms. So uninformed search algorithms, these are search algorithms that do not have additional information about the search state. All right. Remember this, we talked about the states. A state is a state where that state is a state from where agent begins the search. Now that is called the root node. How to get the root node? Okay, like this one here. Like this one here. If this is the first possible solution that the algorithm has to traverse beginning with, it's called the start state, and generally it's called the start state, but because we are describing it like a tree, it's called the root node. Okay, the start state is equal to the root node. Okay, so basically we are saying that in uninformed searches is where the algorithm doesn't have sufficient information about the root node. It doesn't know where to start. All right, or even the search space. In other words, it does not have knowledge about the possible solutions. Okay, it does not have knowledge about the possible solution. It does not know where to start, and it does not have knowledge about the possible solution. So you can actually say that uninformed search algorithms are one of the most complex search algorithms. Why? Because they are working from nothingness. They are working from void. They have to discover, they have to learn. They have to learn their particular problem at hand at that particular point. They do not have any solutions to traverse from. Okay, so that is why we say that it is uninformed. It doesn't know where to begin. It doesn't have a root node, and the reason it doesn't have a root node is because it doesn't have a what? A search space. Okay, so the only thing an uninformed search algorithm has knowledge of, it only has the knowledge of how to traverse the tree. In other words, it knows how to move from one solution to another, but it doesn't have those possible solutions. It just has a mechanism that it is going to use to move from one solution to another, but it doesn't have the solutions itself. It doesn't have a tree as an existing tree, and it also doesn't have a what? It doesn't have a search state, all right, or a start state. That is also called a blind search. Why? Because it begins from nothing. All right, it begins from nothing and then it keeps on generating solutions. Okay, so there are various types of uninformed search algorithms: breadth first search algorithm, depth first search algorithm, depth limited, iterative, and uniform. So these are the various types of uninformed search algorithms: breadth first, depth limited, iterative deepening, and iterative deepening depth first, and uniform cost search algorithm. Now, before I continue, is there anybody with any question so that I continue? Any question? Any question before I continue? Any question? Juma, Dennis, Bashir, Davis? Any question before I continue? All right. Suppliers can be brought to customers. Suppliers and buyers work together without buyers. All right, then let's continue. So these are the types of uninformed search algorithms: breadth first, depth limited, iterative deepening, uniform, and bi-directional search. Now let's begin with breadth first. As the term suggests, as the name suggests, breadth first, it is a search strategy that traverses a tree over its breadth before going to downwards. All right, so this is how it works. Now let me share a screen. Let me just use what we already have here so that we can save on time. Now, breadth first is one that does this. First of all, it does not know possible solutions. It doesn't have possible solutions. So it has to do what? It has to generate possible solutions. Okay. And what generates possible solutions? It's a function, it's a mathematical function, okay, that generates possible solutions. Okay. So those now possible solutions, of course, it uses things like probability and calculus to generate possible solutions, okay, or to generate a search space, because it doesn't have a search space, okay, for any given problem. So what it does after it generates a search space for itself for a given problem, it begins to search through the space it has created in a breadth first fashion. What is the breadth first fashion? Breadth first is like, now look at these nodes here. There are these nodes here that we are given here. So it has generated this search space, okay, this tree. It's called the search tree or the search space. It will begin from here, the root node or the start state, and then it will begin and it will traverse and go to here, then it will go to here. So before going to the possible solutions under A and branch out A to B, or before it digs down A and it digs to C and C to E and E to K, what it does, it goes S to A and S to B. Then it searches A to C and A to B. It searches B to G and B to H. Then if it has not yet found an optimal solution, it continues to search C to E and C to F, D to something else and D to something else, G to I. All right. If it has not yet arrived at a solution, it comes and searches at F. F to something and F to something. It has not found a solution. Then it comes to C to E. C to E, it has not yet found a solution. So it goes to E to K and E to another. Okay. So in other words, as the name suggests, it searches using breadth technique. In other words, it expands through the possible solutions from using the breadth of the search space. It does not go deep down. It goes through the breadth first, and then it uses the breadth to go deep down. Okay, so it searches through everything. So if from one particular node there are 100 others under that particular one node, it will not pick one of the 100 and search deeper down through that one of the 100 nodes. It will go searching through the different 100. If it doesn't find one optimal solution, then it starts over with the node 1 of the 100, and then it goes down. If this node 1 also has 100, it also goes through all the 100. So it's not that it picks one, digs down, picks one, digs down, picks one, digs down. No, it takes a node, it picks all the nodes under it. Then if there is no solution, it's no optimal solution. If there's no optimal solution, it picks one of them and then digs down. Then it checks throughout the breadth of that node if there are other nodes. Okay, so that's how the breadth first technique, breadth first technique works, by going through the breadth of the search space or the search tree. Okay, so what are the advantages? The advantages of breadth-first is that it will provide a solution if any solution exists. Why? Because it searches widely. So it is able to determine a solution. You know, one thing about breadth first or depth first, let me just hint something about depth first. You know, in depth first, it's going to pick one node and go deeper down that node, meaning that it may find in one of these nodes that it has gone deeper down, there is one that is optimal. But remember, it has not tested which ones. It has not tested the others along the breadth. So it may come up with a solution which is optimal, but it is not very optimal compared to if it had searched all the nodes in the breadth. Okay, so that's why we are saying that one of the advantage of the breadth first is that it will provide an optimal solution. Why? Because it searches widely. Okay, then if there are more than one solution for a given problem, this algorithm will provide the minimal solution which requires the least number of steps. Okay, so what this means is that if it searches through a particular breadth, a particular level in the tree, because it's using the search space is always organized in a hierarchy. All right, like a tree, like branches. So what this point means is just that if it goes through a particular level of solutions, it will pick on a solution that it doesn't have to go through over and over. Therefore, it will take the least possible time. Therefore, meeting this criteria of time complexity. Okay. Solution. So minimal solution just means okay, sorry, it's not about the time, but it's about the solution which requires the least number of steps. Okay, and then the disadvantages that it requires a lot of memory. Why? Because it has to traverse through the different levels. Okay, it has to traverse through the different levels. So if the root node has 100 levels, like let's say it has 100 levels, okay, like it has level 1, there are here we only have 2, all right, for of course for demonstration purposes. But imagine if for a real agent, that algorithm at this level we had 100 nodes or even 1,000 nodes. Can you see it will spend a lot of memory going through each different possible solution and testing and measuring the path cost and using the goal test to measure the efficiency of each node, right? So space complexity is an issue. Right? Space complexity is an issue, and also time complexity is an issue. Why? Because it needs a lot of time if the solution is far away. If it needs a lot of time if the solution is far away. Why? Because it's going to search through every level. It is going to search through. It will not ignore. The thing about breadth first is that it does not ignore any node. It searches through every level. Even if that level has 100 nodes, it will search through all the different 100 nodes. Yet you may find that the solution is actually at level 3. At level 3 at I, you may find that this is the goal node. All right, this is the goal state. All right, It is the goal state, it is the goal solution. But it has gone through this, it has gone through C, it has gone through D, it has gone through everything. Instead, it could have just gone to S and B and then go to G and then find I, which is the concept of depth first. Okay, so you see, the time complexity is also an issue because it has to go through every level, even if that level contains nodes that literally don't have any optimal solution. It has to go through the checking. Now, personally, there are also individuals, humans that normally think that when they are trying to solve a solution, they can't necessarily pick small things and work with them. They have to pick a big thing and then work from there. It's like I think personally, and some of you are like that. If I'm doing a research, I don't generally pick on a topic. I basically pick a book. I don't pick on a topic trying to answer a question. I pick a book because I am detailed. So this kind of search algorithm is normally a detailed search. It's a very, very detailed search because it has to go through all the notes. So, like a human being, I would not pick on a topic or an article. I would not pick an article that focuses on that particular subject. What I do, I pick on a topic. I pick on a book, and then I read that book. I dig down until I arrive to the solution, which again, of course, it wastes a lot of time, right? But that's how some people are modeled. I think some of you are like that. So it's not really efficient, of course. It's not really efficient. But the thing is that, one of the advantages that it is able to traverse through all the nodes checking, meaning that next time it will have a lot of information about all the nodes. Okay, because it has already traversed through the nodes. So the disadvantage of breadth first is what? Time complexity and what? Uh, s- time complexity and space complexity. All right. Time complexity and space complex. So those are the disadvantages of breadth. Now let's look at depth first. Depth first is a recursive algorithm. Recursive just means repetitive. Is a recursive algorithm for traversing a tree or a graph data structure. It is called the depth first because it starts from the root node and follows each path to its greatest depth before moving to the next path. This description is very important. It is called the depth first search because it starts from the root node. It starts from the root node and follows each path to its greatest depth before moving to the next path. Now, this is how depth first looks like. Look at this. So as you can see, this is the depth first search demonstrated here. The depth first starts from the root node. So the root node is the first possible solution. It starts with that. Then of course it tests the path cost for that. It tests the path cost, which is the function for testing the path cost is called the goal test. Okay. So it tests the path cost, then it goes to A. So it will not traverse from S to A, then to S to H. It will first traverse from S to A, measure that, then A to B, measure that, then B to D, measure that. Then it will go back and start from S to A to C. No, it will not start again S to A. S to A was already. It will go now to what? A to C, and then C. Sorry, sorry, just a minute. It will start from S to A, traverse from A to B, then B to D. Okay, so it has already searched S to A and A to B. But remember, A to B, D, and BE have a what? They have a branch. So it will come back and test B to E. If it doesn't find a solution, it come and search A to C. Why? Because C has a level, all right? And then search C to G. As you can see, these arrows, the way they follow one another. Okay, so S to A, S to B, then B to D, then it will check B to E. That's why you see this arrow points this way. In other words, from this level, it has to search every depth. Okay, From B to D, it will then search from B to E. And then it will go to C. So after testing E, it will go to C because kumbuka after ilifika A, haiku branch out because it is not a what? It is not a depth, it's not a breadth first, haiku branch out. So itaruka from E, then it go to C. Then after ruka from E to C, it will now go from C to G. In other words, the idea is that it goes searching at every node to its deepest depth. Okay, at every node to its deepest depth, and then it goes back. If it doesn't find an optimal solution, it goes back to the next level or to the next level in the breadth, then goes to the deepest breadth. Okay, but if it was breadth first, it first goes to the breadth, then it checks one, it goes to the breadth, checks one, goes to the breadth. But this one, it picks one, goes to the breadth, goes to the depth, not the breadth. Picks that, it goes to the depth, all the way to the depth, to the depth, to the depth, until the final depth, the final deepest node is measured. Then if the final deepest node at that level does not have an optimal solution, it goes to the next breadth. All right, so that's how depth first works. So what do you think if the goal node, okay, of course, here the reason why G is highlighted in this manner is because it's the goal node. But imagine if G wasn't the goal node. In other words, it's not the perfect solution, it's not the optimal solution. Not it will skip from where? From G to where? It will skip from G to where? Someone. If it finds that G is not doesn't provide the optimal solution, it will now jump from G to where? This is the deepest node at this level. So it will jump from G to where? Someone? It will jump from G to where? If G is not the goal node, it will jump from G to where? Vivian, Dennis? If G is not the goal node, it is not the most perfect solution. Of course, the reason it is highlighted is because we want to show it like the most perfect solution. But imagine if it was not the most perfect solution, then that algorithm will now bounce back from G to where? It will skip from G to where? Which other node has not been tested? It will pass from G to H. Okay, it will pass from G to H. Why am I saying that? I'm saying that because remember it jumped from S to A. See, it's using its depth. So it's moving from S to A, then A to B, then B to D. And if it didn't find D to be the optimal solution, then it went to E. Because E is the next level. It's the next depth that has not been searched. Then if E is not the perfect solution, then it will go to C because hata ilipofika kwa A ilienda kwa B haikuenda kwa C. So inamaanisha hii breadth bado iko na level. Hii level bado iko na breadth. So if it's not E, then it will go to C. If it's not C, it will dig down to C to G. If it is not G, then it will skip to where? To H. Okay, then begin there, then go to I, then go to K, right? Then from K it will go to J, and that way. In other words, it normally picks a node and goes deep to the deepest level. If it doesn't find an optimal solution in the deepest level, then it goes to the next node in the breadth. Okay, so that's how the depth first works. Now, what do you think is the advantage of the depth first? Somebody, Juma, Vivian, Kimorata, Bashir, what do you think is an advantage of that? Going from one depth instead of going to the whole breadth and testing all the nodes, it picks on one node and digs deep into that node to the other nodes that are underneath. What do you think is the advantage of that? What do you think is the advantage of that? The advantage of that is time. Yeah, Dennis. Yes, Dennis, you are responding. What do you think is the advantage of that?
If I don't see you commenting there, then probably only have written your names down here. Those are here. We have Manya, we have
All right, the advantage of these depth first is that the time complexity. There is time complexity is managed very well. Why? Because it doesn't have to go through the breadth first, all the nodes in a breadth. It just picks on a node and goes down. So it is easy for it to arrive to an optimal solution faster. All right, because imagine in a breadth first, probably the solution is at E. Oh, okay, let's just say the solution is at G. Okay, G is the node that contains the possible, the optimal solution. But then in the breadth first, it's going first to test A, going to test H, going to test B, going to test C, then going to test I, going to test J. But if it was depth first, just go from S to A to C, and C to G. Okay, so it just picks on one. It doesn't have to be B. Okay, it doesn't have to be the left node. It can be any. So it can be S to A, S and A to C. It doesn't have to be A to B. Okay, it can be S to A to C, and C to G. So it has the least amount of time to arrive to the solution. But breadth first will have to do what? It will have to search for every node. It will have to test every node in every level, every node in every level, and that wastes a lot of time. Okay. So yeah, so there is that, and also space complexity. It does what? The advantage is that it is not space or memory intensive. Why? Because it doesn't search through a breadth. It doesn't search through many nodes. It searches through uh, the deepest node. So that one does not take a lot of memory. Okay, and can you see that's an advantage? It uses very less memory. Yeah, and it takes less time. The disadvantage is that there's a possibility that many states keep reoccurring and there is no guarantee of finding the solution. Okay, so you may find that this A contains the same optimal solutions like B and C, and it contains the same optimal solutions like E. So you find that it will go through this depth, but it keeps repeating through nodes that are descriptive of the same solution. All right, so that is one of the challenge, that there is a possibility that many states keep reoccurring. Okay, also this algorithm which goes for deep down, and sometimes it may go to the infinite loop. What we are saying is there are some such spaces that don't end based on how complex or how simple that problem is. There are some such states that don't end. All right, so what if it picks on a particular, it uses depth first, and it does what? It goes through the depth of a node, and that node goes on to different levels and it never ends. It's like an infinite loop, like the way you can say while x is less than 10, output x, right? So it keeps outputting 10, 10, 10, 10, 10, 10, 10, 10, 10. It never ends. Why? Because you have coded that while loop is an infinite loop. You have to say less or equal to 10 or something like that. I think you understand the concept. So it can be an infinite what? It can be an infinite loop or an infinite node. It can be an infinite search space, basically an infinite search space that doesn't end, especially if it is for a complex problem. So if it is an infinite search space, then it picks on a node, it will keep going down and down and down, and it's never arriving to the greatest depth. Yet probably the solution was just here. Probably the solution was at H, but ilichukua A ikaenda B ikaenda D, kutoka D ikaenda huko kwingine chini 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 chini, and it's never arriving. All right, so and probably the solution was just here at H. So that's another problem for depth first, is that there for some search spaces it can generate a search space that is infinite. It has very very many number of nodes within a node. Okay, that's one of the disadvantages. Okay, all right, and then number 3, depth limited. Now, depth limited is basically a depth first approach. Oh, sorry, Mulongo, can the states enter into infinite loops in DFS? Yeah, that is what we have said. There can be not, it is not a loop really, but it is an infinite search space. It is not a loop, it is an infinite search space, meaning there are many possible solutions. In other words, those possible solutions are too many, they don't end. All right. So Bashir, there can actually be an infinite search space using a function. You see, it's a mathematical function. So a mathematical function can come up with an infinite number, all right, or an infinite series of numbers. Because a mathematical function, it's like calculating from 0 to infinite, 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9. So you see, in in math, numbers can go to whichever level, all right, and when it goes to a lot of levels that cannot be worked out, then we say that's an infinite scenario. So here we are saying that this algorithm can generate a search space that ends up having infinite number of nodes. Okay, so it can go from A to B, B to D, D to F, F to another, down, 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 and it never arrives because that particular search space has an infinite number of nodes. Okay, so that's what we are saying. It can actually have a search space can be infinite, and that can be a problem if we are using a depth first, because it will pick a node, go to the deepest depth, and it never arrives. Yet the solution probably is just somewhere at the top. Okay, so now Bashir and everyone in the class, the solution to that particular problem in depth first search, the solution to that, if the algorithm, if we still want to use the depth kind of search, but because to address the issue of infinite search spaces, then the solution to that is what now we call the depth limited. Depth limited is where there is a control measure where it will use the depth first technique, but at going to a particular depth, if it goes to a particular depth and still there is a solution is not found, and you see there is the issue of time complexity, so it is wasting a lot of time going down an infinite search space. Yeah, we talked about time complexity, right? So it is wasting a lot of time going down an infinite search space. So the because of the issue of time complexity, then it will have to use a particular measure to do what? To limit how deep it can go into the nodes. All right, how deep it can go into the nodes, so that now if there is no solution that has been provided, then it will cease going deeper and jump into the next level. So this is basically the solution for depth first. The solution for depth first, because of the case for infinite search spaces, is the depth limited. As the name suggests, it can only go to an agreed or a required depth. And if there's no solution being found, it does what? It goes to the next level instead of going deep and deep, and it never arrives. Okay, so it's called the depth limited, a depth that is limited. I think these names are very well named. You're able to understand. So can you see here, depth limited search solves the drawback of what? The infinite path. So you can have an infinite path or the infinite search space, and so the depth limited addresses that problem in that it limits how deep it can go to a node if those nodes are infinite, if that search space is infinite. Okay, so in this algorithm, the node at the depth limit will treat as no successor nodes further. In other words, there will be the algorithm will set a limit to how deep that algorithm will search. So for instance, if it is here, it may come here. Unaona hapa venye sasa now we have depth, it's a depth limited. Ianze S, iende to A, then A to C. And instead of going from C to E, it will now jump from C to D. In others, now it will traverse to the next level without going any deeper or any further deeper to the nodes that are down. Do you understand that concept? So in other words, it has a limit, and that limit is set on a particular, that limit is set on a particular level. So the algorithm itself it may set a level at level 2. It may say that level 2 is the limit of search. Okay, so it cannot go deeper to any nodes if it has not searched through level 2. All right, otherwise it will waste a lot of time going deeper and deeper and deeper. Kumbe solution iko tu hapa kwa J, solution iko level 2, but imechukua CA to C to E na iende deeper, and yet the solution iko huku juu kwa level 2. So basically it sets a what? It sets a limit on a particular level. All right, so it does the depth first, but it only up to that particular level. Then when it arrives to that level, it traverses to the next node, and then unaona from D now to B, because B was not, it was S to A, so B was not tested. So ikimaliza D, so inaenda ina search kwa B, then from B to I. Kama I ina solution, inaenda from I to J. Okay, so of course J now is the optimal solution, what you call the goal state. But if J was not the goal state, can someone tell me if J was not the goal state, now it will skip from J to which one? Ndio iendelee kusearch, it will skip from J to which one? If J were not the goal state, if J were not the optimal solution, now the search algorithm would now advance to which node? From J to, it will now skip from J to which one? Bashir, Dennis? If J were not the goal node, the goal node is basically the node that represents the best solution, which we call the optimal solution. So if J were not the optimal solution, it were not the goal node, it will then skip from J to which other node, so that it can continue the search. It will go where? It will go to E. Davis, is that what you wanted to say? Okay, then it will go to E. All right, it will go to E. In other words, if it starts from S to S, see, there is a limit. There is a limit to the search. So if it goes, and the limit is level 2, so if it goes from, and it's still using depth first, so if it goes from S to A, all right, then A to C, it has arrived to this level, so it cannot go any deeper further. So it is now supposed to search the other deep nodes in that level. Yeah, so it will skip to D. Then it finds that D is not a goal node, then it will skip to B, because B was not searched. All right, and then it will now skip from B to I, and then if I is not a goal node, skip from I to J. All right, then if ukiangalia imesearch zote hizi levels zote, they have been accommodated, right? They have been searched from level 0 to level 2, they've been searched. So now it will skip to where? Obviously it will skip to E. Okay, and then it can now go down to from E to another level down here, and then probably there will be another limit, unaona. So kunaweza kuwa na limit ingine huku chini, so the algorithm can set a limit up to 2. So after every 2 levels there is a search limit, after every 2 levels is a search limit. So ikimaliza hiyo level inaenda ina search through the breadth. Okay, inamaliza hiyo level. And kama there is still no goal node that has been arrived to, now it goes to the next level and searches deeply. So ikimaliza J itaenda kwa E, kwa sababu all these levels have been searched. So it will go now to E, then from E to another, and from E to another, that way. Okay, I think now you understand how that works. So depth limited is a depth first that has a limit to how deep the search can go, in order to address what? The issue of infinite search spaces. Because if there is an infinite search space that has been generated by the algorithm, that means that what will happen? It will use a lot of memory, yet it's not reaching any solution. Okay, it's using a lot of memory. The process is working a lot, going deeper into the nodes, but it's not arriving to any solution. So a limit is set so that we do not go deep down in vain. All right, so that it does not go deep down in vain. So the advantage of this search, of course, according to explanation, is that number one, it addresses the issue of space complexity. So in the case of an infinite path, the memory is not going to be used up, all right, by a simple search. It's not going to be used up by a simple search because we have to go down to deep into nodes that never end. So the problem of space is addressed. Also the problem of time is addressed. Why? Because by setting the limit, we know that we don't have to search all through. We can actually go to the next node in that particular level. We can go to the other node so that we don't waste time going deeper and deeper. So time also is so basically what we are saying is that depth limited combines the advantages of the depth first and addresses the disadvantages of depth first. So if the advantages of depth first, remember depth first, the advantages of depth first was less memory and less time. Basically it will also have less memory and less time, and it will also address this problem of recurring nodes. So it doesn't have to go deep into nodes that keep repeating themselves, or that have the same range of probability. You can have nodes that have the same range of probability: 0.1, 0.12, 0.1112, 0.1132. Those are normally nodes that have what? That have the same range of possibility. So it does what? It addresses the problem of recurring nodes. So if instead of going into nodes in deep down into nodes that have 0.132, 0.142, 0.112, deeper and deeper and deeper, it can now go into the next node in that level, like 0.23. Now it has skipped to another level. All right. So it doesn't have to keep going into recurring nodes. Right together. Yeah. And so of course the issue of infinite loop is addressed. All right, so that is it about depth limited. Now uniform cost search. Uniform cost search is a searching algorithm used for traversing a weighted tree or a weighted graph. We are going to discuss what this means. This algorithm comes into play when a different cost is available for each edge. The primary goal of the uniform cost search is to find a path to the goal node which has the lowest cumulative cost. Uniform cost search expands nodes according to their path cost from the root from the root node. This is not from, it's from the root node. It can be used to solve any graph or tree where the optimal cost is in demand. A uniform cost search algorithm is implemented by the priority queue. It gives maximum priority to the lowest cumulative cost. Uniform cost is search is equivalent to breadth first if the path cost of all edges is the same. All right, let me explain what this means. In the previous concepts, in the concepts we were talking about, the search space, the search tree, the goal node, the root node. We discussed a concept called the path cost. All right, the path cost is basically the cost of arriving to an optimal solution. I want us to look at that again so that we can actually apprehend what we are talking about. The path cost is a function which assigns a numeric cost to each path. All right, a numeric cost to each path. Now, what the uniform cost search algorithm does is that it generates a search space. Or again, it's a blind search. It's an uninformed search, so it doesn't have a search space of its own. So of course, like any other, like the breadth first, depth limited, it has to do what? It has to generate its own search space. There are no pre-given search spaces. So the depth, the uniform cost, it first generates the search space. Then, instead of searching using breadth first, like from S to A, then S to B, or using depth first, like S to A and A to C and C to E, or using depth limited, like S to A and A to C, and then S, C to D, and D to B. Instead of doing that, it does not use a direction of search, it uses a cost of search. In other words, it picks on the nodes that have the minimal cost. Now, the minimal cost is basically, for instance, if it is a self-driving car, there are those particular solutions that are going to least impact on the environment, and also the fuel being used, and also the least amount of damage to that particular car, and also the maximum amount of safety. Now, that kind of solution is the solution that we can say it has the least cost. All right, it will not cost the agent a lot. That is what we are saying. Okay, the costs. All right, it's a function that assigns a numeric cost to a particular solution. So basically what it does, it goes from one node to another, and then this node to this one. Now, if this, let's just say, if this goal node, and not goal node but the root node, it has a 50% cost rate, 50% cost rate, then it moves from S to A, it finds A has 53% cost rate, it will move to C. If it moves to C and finds C has 60% cost rate, you see, we are trying to find the one which has minimal cost rate. Okay, if it finds C has 60% cost rate, of course it means that E and G, they have higher cost rates. Okay, so ikifind C iko na 60, itaachia hapo. Okay, itaachia search hapo, then iende ikatest D, ipate D iko na 43. All right, so if D has 43, you see now D has now the minimal cost. Now hii ilikuwa na 53, iko na 50, iko na 60. So which one was the least? Si ilikuwa 50, but now 43 is the least, so itatumia D. So iende ikatumia D, ipate D iko na 43 of course, and then ipate F iko na 40. Ikipata F iko na 40, itaenda ikitraverse, itatumia F kutraverse. In other words, the idea here is that it uses the particular node that has the least cost, and then it traverses through that one. If it finds through that node there is another that has a high cost, it goes back to the one which had the least, and then in end in a search 10. All right, so basically the uniform cost search is a search algorithm that picks on the nodes that have the least cost, that have the least path cost, and therefore it doesn't just search using a direction, it doesn't search using levels or depth, it searches using cost. So the one that has the least cost is the one that is picked. So basically, you may actually find that the uniform cost search can be haphazard. Haphazard. Why are we saying it can be haphazard? Because it may find one of the nodes. If, for instance, let's say S has 50% cost, A has 53, right? C has 60. So which one has least? It is S, right? Or let's say S has 53 and this one has 50. So the least one has what? The least one is A. The A has 50%. So itarudi kwa A, because hapa imepata hii ni 53. So it doesn't have to traverse through C, because C already has a high cost. Okay, it is trying to find the one which has least cost. So itarudi kwa A. Okay, so ikirudi kwa A ita search, because this one should lead to another, because the one that has the least path cost should lead to another that has the least path cost. Okay, so if it traverses from A to D and E ilikuwa na 50, and then it has found this one has 43% path cost, yeah, then it will use D to traverse, then it will now go to F. So it will use the mechanism of both breadth first and depth first. Do you notice that? It will use the mechanism of both breadth first and depth first, because it is using an haphazard approach based on which one has the least path cost. So it moves from 40, and then it moves to this one, and this one has 48. This one has 48. iko na 43. Then it goes back to G using the depth approach, and then it finds this one as 40. So itatumia F ama itatumia G? Itatumia G. Alright, then it will traverse now downwards using G. Then ikipata G zake zenye ziko chini ya G, at level 4 iko na 50 na iko na 60, ita skip back to where? To 40, and then it will skip back to 43 and skip back to 50, irudi hapa kwa B. Are we together? Because it's trying to search the one which has the least, and then the final one which has the least path cost is the one which is picked. So that is why it uses a very haphazard kind of approach. It's a very haphazard kind of approach, right? Haphazard in the sense that it will use both breadth first and depth first and even depth limited, but basically it will just be testing for the cost. It is not uniform cost search is not about the direction of the search, it is about the cost of the search. The one which has the least path cost is the one which is picked. Okay, so it has to search through. The node which has the least is the one that is traversed. When I say traverse, it's basically passing from one node to another. Traversing is basically what we have here. You can see there. Then the arrows are the direction of traversal. Okay, so traversing is passing between different nodes. Okay, so the node that has the least path cost is the one that is picked, and then traversing happens continually through that node downwards. All right, then it finds another. If it finds other nodes, if it finds this particular node has other nodes that are more expensive, let us use cheap and expensive nodes that are more expensive, it goes back to the last node that was least expensive. So it's like you going to the market. So you go from one buyer, you find they sell a shirt at 200. You go to another, it's the same brand, another buyer selling the same brand at 300. Right? Then you go to another brand, you find it's 350. Utarudi kuhu mwenye ni wa 200, right? Then you go to the next one, you find they sell at 150. So what you are just trying to do, you're trying to use the cheapest seller to lead you to the cheapest seller. Right? So basically that is basically what we are saying. We are using the cheapest node to lead us to a more cheaper node. If we don't find a cheaper node, so if I've used this seller 150 and then niende kwa the next other kibandas that they may be selling at 150, 130, 170. So I am within nodes of that particular range. So I've used this cheaper seller to lead me to other cheaper sellers. Okay, and so I go to 150, I go to 130, I will go to another seller that even sells at 120. I can even find another one who sells it at what? At 100. So basically, cheap uniform cost uses the cost of a node, and the one which has the cheapest cost is the one that is picked to lead the traversal, to lead the direction of the traversal. And that's why we are saying it's an haphazard kind of approach. Okay, then iterative deepening depth first. Okay, what are the advantages? The advantages of uniform cost search is that the search is optimal because at every state the path with the least cost is chosen. So you can have here in depth limited, you can have you can search through the depth, and because you are not looking at the path cost, you will go through different depths, leaving the one which has probably B is the one which has the cheapest, but because you have to test, you have to go through every level. So you're going to pick on nodes that don't have what? The least path cost. So it's like, so depth limited itaenda ikisearch through all the depths and then irudi hapa kwa B yenye ilikuwa na so ni kama inaenda ina search yote hadi chini kabisa, and then it goes back and picks the one which had the least path cost. So depth first, depth limited, and breadth first is like looking for vendors. Now unaenda unawatafuta, you sample out all of them, then now you go back to the one who was cheapest, which is not optimal. But this one, you just look for the one which is cheaper. Unaenda unaangalia ni gani anauza wa 200, unapata mwingine wa 350. So who are 350, you will now just know that who are 350, the other places they are selling at the same price. So unarudi kwa huyu wa 200, they guide you. So kama we are 200 at this particular place, he's selling at 200, means that at the same, around the same area. Of course, if you go shopping, you know how these things normally go, right? Yeah, you go there, find that there are others which are cheaper, right? And then you search through others which are even cheaper, right? So basically, uniform cost is optimal because it uses the least path cost, and it doesn't have to do what? It doesn't have to pass through all of them. Okay, when it finds the one which has the least path cost, then it does what? It picks on that. The iterative deepening is a combination of depth first and breadth first. The iterative deepening is a combination of depth first and breadth first. Now, because you have these notes, I'm not going to explain because I've already explained depth first and breadth first. So basically, the iterative deepening combines the strategy of depth first and the strategy of breadth first. And already we've discussed depth first and breadth first. So I'm going to task you as a responsibility to read about the iterative deepening. So basically what that means is that if it combines the strategies of depth first and breadth first, then it combines what? Both the advantages and the disadvantages of depth first and breadth first. Okay, so I don't have to keep teaching you that because I've already taught you depth first and breadth first. So it's basically a combination of the two. Okay, and you are going to, as there are diagrams here, so you're going to actually study that diagram and also the key that is given here, okay. So the iterative deepening just works this way. It will first start from A, then go A, B, C. Then from A, B, C, it is going to go to A, B, D, E. Do you get that? Okay, A, B, D, E, C, F, G. Then from that, it will go to A, B, D, H, I. All right. So in other words, it basically combines the mechanism of depth first and breadth first, and I'm going to task you to read about. That because we had already explained depth first and breadth first. So let's finish up with bidirectional. Bidirectional search. It runs two simultaneous searches. One from initial state called as forward search, and other from goal node called as backward search to find the goal node. Bidirectional search replaces one single search graph with two small subgraphs in which one starts the search from the initial point of the initial vertex and other starts from the goal vertex. The search stops when these two graphs intersect each other. I think you can already visualize this statement even before you go to the diagram or to the tree. Basically, bidirectional can use such techniques such as breadth first, depth first, and depth limited. Now, this is how bidirectional search works. For instance, this is the root node, and this is the goal node. The goal node is basically one of the nodes which can be the optimal solution. So basically what it does, it uses two directions from searching. In answer from root node, you remember that all the others, we have been beginning the search from the root node. Now this one, we begin the search from the goal node. Now let me just explain using layman's language. Like if you go with two people to the market. So you go with two people to the market, you are looking for the cheapest. You are looking for the best shirt or the cheapest shirt or something. So what you do, you pick, you are two of you. You tell your friend, weanza ile point, na mimi nitaanza hii point. Okay? And then you go searching and searching and searching. So you go sampling and find out and picking reports of the cost at every particular vendor, and then me I also go around and come back mahali tutapatania. All right, mahali tutapatania. Now that's where we are going to decide which is the best vendor. So do you understand how that works? So we kind of divide ourselves. We are two of us. You search from one point and I search from the other point, and we come when, so where we intersect is where the search ends. And then now we can determine who sells the best. So if you tell me you found a seller who sells a shirt at 200 but it's the best brand, I tell you I've found a search at 150 and it is that particular brand, the same brand, then we are going to go with my search, with my finding. Okay, so that's how normally the bi-direction, that's what we call bi-direction. In other words, the search does not only start from the root node, it starts from the root node, it can also start from the end node. Okay, and where the search intersects, that's where the search stops. Okay, so basically it also, we say that one of the advantages is it is fast. Okay, kwa sababu if we are two of us we have to search a whole market. Wewe unaweza search nusu na mimi ni search nusu tukuje tupatanie mahali, so it's fast rather than tutembee pamoja si wote, we start at point B and then we search all of us going through every vendor until we finish up the market. We complete searching through the whole market. It's slow, but it is fast because both of us, we have divided ourselves into the market into two. We are two of us, we have divided the market into two, right? So it's fast to search, and it also requires less memory. Why? Because we are not searching from the root node into the different nodes. We are searching from two different points, so it requires less memory. But one of the disadvantages is that the implementation is difficult. Why we think the implementation is difficult? Because how, for instance, now one of us has searched from one level and the other one has searched from another level. Okay, so there are two levels. Do you notice that at the point where we are going to intersect, that point, at the point where we're going to intersect, we are going to all of us go back to where one of us was. Isn't that right? Or all of us find that all of us realize that we have not found the best shirts that we need. So we found 200, but it's not a good one, and have found 150, but it's not a good one. So what do? We'll have now to get together and apply the other searches. All right, like bread first. We now go back together. We take every vendor one by one. So it's a very difficult. It's a very difficult approach to use. Also, the other reason why this approach is difficult is because determining the intersection node is difficult. The function that has to determine the intersection node can be difficult to determine. Okay, this particular node here that should determine where your search and my search should stop. This particular function, it is difficult to complete that function, right? So that is why it is difficult to implement. And also in bidirectional search, one should know the goal state in advance. In other words, we already know what to expect. So we already know the solution that we need. Why? Because you're looking for a shirt that ranges between 200. I'm also looking for a shirt that ranges between 200. So all of us know what the goal, what we need, and the brand. And that is why it is hard. So imagine we already do not know the search space, and we do not know the states because it is a blind search. But yet we are still required to know the goal. That is difficult. All right. So that is why it is difficult to implement the bidirectional search. So that's what we have for an informed search algorithm. In the next class, we are going to discuss informed search algorithm, and that is going to do us good. So I require that there are those notes that I shared, the notes that I shared in the previous classes, those notes that I shared in the previous classes. Let me see if we have these notes so that I can know if you are able to read. No, I've not shared. I've not shared the notes. Um, I'm going to share these notes and also share the page numbers which you are expected to read so that you may read whatever we have had this morning. Whatever we have had this morning. So that then brings us to the end, because if we begin with informed search algorithms, it's going to take us a while. So that brings us to the end of our lesson today. Is there any questions? Have you understood? Any questions? Any questions that you need to ask? So if there is no question, then that will bring us to the end of our class today. So have yourselves a good day.